Welcome back, mathematicians. Today we're going to focus on 4.4 and 4.5. So first, 4.4 is the fundamental theorem of calculus. So we just went over definite integrals, and we talked about how we don't quite know how to evaluate them yet. We know how to evaluate some graphs just by like pictures that we knew, like we did like a semicircle and some rectangles, and we know how to find the area of those things. So first we need to talk about the mean value theorem for definite integrals. So we're given this little handy dandy theorem, and this should look similar to the average value that we talked about last section. So if f is a continuous function on AB, then there's some point C in AB such that the function value is going to equal 1 over b minus a times the integral from a to b of f of x dx. Right, and last time we called that the average value of f. So basically mean, we also called it the average value. Mean are the same thing. So why is this true? Why do we know that this is true? So remember the min and max inequality, where the minimum of f is denoted little m and the maximum of f is denoted big M. Then we can take the rectangle created from the constant line of the minimum and the constant line of the maximum, and we get that the integral between the integral of AB of f of x is going to be bounded between the minimum times BA and the maximum times BA. B minus A, excuse me. So if we divide each side by B minus A, we get that the minimum value of the function is going to be below the average value, and the maximum value is going to be above the average value, which that makes sense, right? So since f is continuous, there's going to be a number C in AB such that f of C equals, I wrote it somewhere. Equals that average value, right? And we know that because of the intermediate value theorem. All right, so we can kind of see with this really bad drawing. The area in blue, that's going to be our integral. And then f of c, the area below that, those areas are going to be the same. All right? So that's just the mean value theorem for definite integrals. Pretty similar to what we had with derivatives as well. All right? So now we're going to move on to how to evaluate definite integrals and kind of the main two theorems in calculus. And I spelled calculus wrong. Ooh. There we go. Okay. So there's the fundamental theorem of calculus, and it actually has two parts. So part one is the lesser used theorem, in my opinion, but it's actually probably the most interesting one. So if f is continuous on AB, then big F of x is going to equal the integral from f of a up to x of f of t dt. So I'm evaluating this antiderivative from a up to this variable x. So see that these guys match right here, okay? If that's continuous on AB and differentiable, then the derivative is going to equal d dx of a x f of t dt, which should equal f of x. So this theorem is kind of talking about how do I take the derivative of the antiderivative and what comes along with that. All right? So let's put this into action a little bit, because it's kind of being like, well, duh, isn't the derivative like whatever? There's some tricky parts of it. So if we use the fundamental theorem to find dy dx for these three integrals, so if y equals the integral from a to x of t cubed plus 1 dt. So in this case, we had that f of t is equal to t cubed plus 1. All right. Well, then we should just be able to, this pretty much matches what we have up here. I have an a down here, I have x up here, I have a function of t dt. So this is just going to equal f of x. So instead of having a t there, I'm going to have an x, which is getting me x cubed plus 1. These next two aren't going to look too much like the fundamental theorem that we have above. So now I have x on the bottom and my number 5 on the top. So what do we do now? Well, order of integration we talked about last time. I can rewrite this and say that it's equal to the negative of 5 to x of 3t sine of t dt. Perfect. Now I can apply the fundamental theorem to the integral. So I get that, oh, sorry, this is dy dx. It's going to equal, so this is 3t sine of t is going to be f of t so it's going to be negative, oops, 3x sine of x, all right? Because we just applied the fundamental theorem onto the integral, not that negative, okay? Beautiful. So the next one is probably one of my favorite examples. So we don't have x here, we have x squared, which is pretty weird. So we can, just like we did when we ever had chain rule, because right, we're taking a derivative. So if I'm finding dy dx, I can make u equal to x squared. So that when I take dy dx, I'm going to take the derivative of u wait, hold on. Yeah. I'm going to take the derivative of y with respect to u, and I'm going to take the derivative of u with respect to x. There we go. Okay. Okay. So we're going to rewrite, let me move this around a little bit. So we're going to let u equal x squared, so that this is just going to be from 1 to u cosine of t dt. All right, and then so dy dx is going to equal, sorry, dy du is going to equal the derivative of 1 du cosine of t dt times du dx, right? So now this integral looks like the fundamental theorem of calculus. So now I can apply it there, and I'll get, oops, sorry, cosine of u times du dx is going to equal, let's leave it du dx right now, all right? And we were given the problem in terms of x's, so we need to sub in for our x's back in. So u was x squared, so we're going to do cosine of x squared times the derivative of x squared, which is 2x. All right? And that's how you can do it when one of the bounds isn't necessarily a, whatchamacallit, what am I thinking of? And with it isn't x squared. So even if I had probably like 1 plus 3x squared, I would do something similar like this. All right? So the fundamental theorem of calculus part 2, this is where we get to, it's also called the evaluation theorem, how we evaluate a definite integral. So if f is continuous over ab and big F is any antiderivative of little f, remember because big F can be any different by a constant, on AB, then the integral from a to b of f of x dx is going to equal big F of b minus big F of a. All right, so I'm going to find the antiderivative, and then I'm going to plug in my upper bound and then subtract my lower bound from that. All right, we also sometimes will write it like big F of x and then a line a b. This means the same exact thing. So if you see my notes later on, that's how a lot of us write it. You can feel like a really cool mathematician writing it that way. It just means evaluate at when you see something like that. And that's just a straight line. Okay? So let's do a few more examples. We're gonna evaluate the following integrals. Let's leave the fundamental theorem up. There we go. So the integral from 0 to pi of cosine x dx. Well, I know that cosine of x is the derivative of sine of x, so I'm going to write that this is equal to sine of x from 0, evaluated at 0 to pi. All right, and that's going to equal sine of pi minus sine of 0. Oops. Oopsie. Sine of 0 equal to, sine of 0 is 0, and sine of 0 is also 0. Or sine of pi is 0, that's what I meant to say. So those equal 0. So perfect, great. All right, this one. So I like to rewrite these, the integral from 1 to 4 of 3/2 times square root of x minus 4 divided by x squared dx. Oops, I need that. There we go. I like to usually rewrite these with numbers as the exponents and everything up top, because that just helps a girl out. All right, cool. So these are just going to give us some power rule. So I'm going to add 1 to the exponent to x to the 1/2. So that's going to be x to the 3/2. I'm going to keep my coefficient, and then I'm going to multiply by the reciprocal of my new exponent, which is 2/3. And those will cancel out. Next step. All right, minus 4 times x to, so the negative 2. I'm going to add 1, and that's going to be -1, and then I'm going to divide by -1 as well. Perfect. And then we can never forget our plus c. Actually, just kidding, we can. The reason we don't have a plus c here is because if you think about it, when we, there we go. If we have like f of b minus f of a, so it's like f of b plus c minus f of a minus another c, those c's cancel out. So that's why. Sorry, I was trying to really make sure that you guys don't forget your plus c's, but you don't need them in definite integrals because they kind of go away. All right, cool. So now let's simplify a little bit before we plug in 4 and 1. So this is just going to be x to the 3/2 plus 4x. That looks like a lot easier to handle than all that hoo-ha that was there before. All right, cool. So I have 4 to the 3 halves plus 4 times 4 minus 1 to the 3 halves minus, because that negative goes through, 4 to the 1. So square root of 4 is 2. 2 cubed is 8. So we get, ooh, wait, this is x to the negative 1. Oopsies. So that's 4 over x, my bad. Not 4 times x. We all make mistakes. So this is going to be 8 plus 1 minus, I can like group those together, minus 1 to minus 4. One plus 4 is 5. So that's going to give me 9 minus 5, which is 4. There we go. Okie doke. So we simplified, or not, kind of unsimplified, the integrand to help take the antiderivatives, found the antiderivatives, rewrote it correctly, and then plugged in 4 and subtracted when we plugged in 1 and simplified. All right. So next one. Integral from 0 to 1 of dx divided by x over 1. We often write it like this, but this also just means the integral from 0 to 1 of 1 over x plus 1 times dx. Same exact thing, just the dx. It's more simplified the first way. All right, so I know that 1 over x's derivative is ln of x. So 1 over x plus 1, I'm pretty sure that's going to be ln of x plus 1 as well. And I can always take the derivative at this point and double check. So if I look at this guy, I just 1 over the inside times the derivative of the inside, 1 over x plus 1 times 1. Perfect. All right, and then I need to evaluate it from 0 to 1. So that gives us ln of 1 plus 1, oops, not plus, minus ln of 0 plus 1, so we get ln of 2, minus ln of 1, ln of 1 is just 0, so we get ln of 2. Ta-da! Not too bad, right? So that's how we're going to evaluate definite integrals from now on. So I said this earlier, definite integrals are going to give us a number back out, f of b minus f of a. Earlier we saw how we're going to be left with x's, and these are still functions. That's because a and b aren't numbers there. So when we have numbers as our bounds, that's when we're going to get a number back out instead of a function. And if we don't have any bounds, we're definitely going to get a function back out. All right, so some fun applications. So the integral of a rate. So we define the antiderivative big F of x such that little f of x is equal to the derivative of big F of x, right? That's the whole point of big F of x. If we replace little f of x in the fundamental theorem of calculus, we have that it's going to be the integral time of big F of x prime dx, and that's going to equal, oopsies, f of b minus f of a. All right, so that gives us the following theorem, the net change theorem. We talked about this a little bit when we talked about displacement and total distance, and we're about to revisit that as well. So the net change in a differentiable function, big F of x, over over an interval a, b, is the integral of the rate of change. So meaning that f of b minus f of a, the net change of that function, is going to be the the integral of that function's derivative. All right. So a few examples of that is if c of x is the cost of producing x units of a certain commodity, then c prime is the marginal cost. Marginal cost is the change in price to make just one more product, right? So if I take the antiderivative of this and apply the fundamental theorem of calculus, I'm going to get c of x2 minus c of x1. Well, that's going to give me the difference in making one product versus, or x2 products minus x1 products. All right. So then, if an object's position s of t moves along the coordinate line, its velocity is v of t, which is just the derivative of s of t, and then displacement is going to be v of t2 minus v of t1, right? Where I ended minus where I started, right? If I start at home, I go to Target, and I come back, and I'm right here again, I didn't move at all. 0. But if I go here, I'm at home, I go to Target, and I go to Starbucks, I'm going to have a different displacement. But we also talked about the speed, or the absolute value of v of t, being the total distance traveled, right? If I'm still back at home, but I did travel 10 miles, those are two different types of things. How do we calculate total distance traveled with the integral? Because absolute value makes everything a little bit trickier. So we can do that by finding the total area. All right, so how do we find the total area? Well, let's look at sine of x on 0 and pi. That's kind of the best way. Well, we talked about how last time that this is going to be a positive area and this is going to be a negative area. But I want total distance. I want the absolute value. So I need to figure out how to differentiate between the green area and the red area. And I want to make that red area not a negative value, all right? So if I just look at the definite integral over sine of x from 0 to 2 pi, that's going to give me negative cosine of x from 0 to 2 pi. Well, that's just negative cosine 2 pi plus cosine of 0, right, minus a negative. And that equals negative 1 plus 1, and those cancel out, all right? So we need to split 0 to 2 pi into two pieces, from 0 to pi, which is this green area, and from pi to 2 pi, that red area. Because we want to separate them so that I can just focus on the area on the green and just the area on the red. So notice that we, each of the endpoints where we split it, 0, pi, 2 pi, those are all where sine of x equals 0. It just so happened that the endpoint or interval is also where the function equals 0, but really important, that pi, that's where we can split it in half, is when sine of x equals 0. So if I do each of the each of the integrals, we'll get negative cosine of x from 0 to pi this time. And that's going to equal negative, let's leave the negative out, cosine of pi minus cosine of 0, which is equal to negative 0 oh, wait, not 0. cosine of -1 minus 1. So negative 2, which is a positive 2, right? And we expected a positive number looking at the picture. Well, what about from pi to 2 pi? We should expect a negative number. So we get negative cosine of x from pi to 2 pi. Draw my line. So negative cosine pi minus cosine of 2 pi. Wait, no, backwards. 2 pi. Yeah, 2 pi minus pi. There we go. And that's going to equal -1 minus a -1, so -2, which makes sense. We expected a negative version. So if I want to find the total area, whatever area gave me a negative, I'm going to make positive, right? So I'm going to take the total area, and that's going to be 2 plus the absolute value of -2, which will give me 4. Absolute value of -2 is just 2. All right. So we have a summary of kind of how to find the total area. So to find the area between the graph of f of x and the x-axis, it's another way of phrasing find the total area over the interval AB. We're going to first subdivide AB at the zeros of f. So we did that at pi for sine. We're going to then integrate f over each subinterval. And then we're going to add the values together, but we're going to add the absolute values. Just like how we added 2 plus the absolute value of -2. All right, so let's do another example where it wasn't so even on the other sides. So we're going to find the area of the region between the x-axis and the graph f of x equal to x cubed minus x squared minus 2x. And our interval is -1 to 2. All right. So first, we need to find our zeros. So and then, so we're going to say f of x equal to x cubed minus x squared minus 2x. We're going to set that equal to 0. Well, I know each one of these has an x in it, so I can pull that. So I get x squared minus x minus 2. So that gives me that x is 0. And then we can work with x squared minus x minus 2 equal to 0. And I think we can factor that. We don't need to do the quadratic. So minus 2. So we're going to have x minus 2, x plus 1. Does that work? Because we add -2 plus 1. Yeah. Okay, cool. You guys can factor any way that you would like. This is just how I factor. So x equals -2 and x equals 1. So those are our 3 zeros. Well, that's good. That, oh wait, that was wrong. X equals 2 and x equals -1. My apologies. So these two are the endpoints of our interval. Awesome. And so we're going to split -1 to 2 into -1 to 0 and 0 to 2. All right. So now we're going to integrate over each of those integrals. So from -1 All right, so we're going to integrate from -1 to 0 of x cubed minus x squared minus 2x, that whole thing, times dx. And that's going to give us x to the 4th over 4 minus x cubed divided by 3 minus x squared. And we're going to evaluate that from -1 to 0. If I plug in 0 into all of that, I'm just going to get 0 back out, minus, 1 over 4 minus 1 over 3 minus 1. So that's going to be, oh no, that's positive because that was a -1. 0 minus -5/12. And so then that's going to give us just 5/12. Okay, cool. Positive number. That's good. So then we're going to do from 0 to 2 of the same integrand. All right, so it's going to give us the same antiderivative. But now we're going from 0 to 2. All right, so 2 to the 4th is 16. So 16 divided by 4 minus 8 divided by 3 minus, what is that, 4? 4 minus 0, because 0 minus 0 minus 0 is all just 0. Alrighty, so this equals 4 minus 8/3 minus 4. So that's just going to give us -8/3. Perfect. So now I want to find the total area. So we're going to do 5/12 is already positive. So we're going to keep that positive plus the absolute value of -8/3. So +8/3, and that actually comes out to be this beautiful fraction of 37 over 12. 8 times 4 is, 24. 30, yep, okay, 5. Okay, great. 32. So we get 37 over 12, and that's going to be our total area. Okay? Alrighty, so now we're going to talk about section 5.5, which is a really fun one. And yeah, I'll see you guys there.